So today we are going to work on solving some more rational inequalities. You should be able to know how to do those, but we'll review that a little today as well, in case you've forgotten since last Thursday or whatever. But once we solve them, we want to be able to know how to apply the solutions we get in a real world context. And we'll know we'll have it when we can actually self-check our solutions using algebra or technology and that they make sense in context. Okay? Now, before we go on, just like we did with the quadratics, many of these are what I call artificial real world. They don't have to be, and I'm going to give you an example of a real world. At the end of this lesson, we'll talk about that. But we'll go over what the problems are like first, and then we'll talk about a real world context. Okay, something that's actually real. Alrighty, let's get to the problems. So here's a typical rational equation, and then I'm going to turn it into a rational inequality. This problem is a rational inequality. This is a very typical one. It says, suppose that the government imposes a $1,000 per day tax on the bicycle manufacturer so that the daily cost of manufacturing X bicycles is now given by the cost function 80x plus 6,000. Now the average daily cost is given by 80x plus 6,000 divided by X. Why is that? X represents the number of bicycles. So if you take the cost divided by the total cost divided by the number of bicycles, that gives you the average cost for each bicycle, right? So the question is, how many bicycles must be produced each day for the average cost to be no more than $100? All right? There's the inequality introduction. All right? Now, your example in the lesson does this with a gravity problem. But the problem in the exercises doesn't do this, and I'll show you why, what the difference is. But this says no more than $100. That means you have to be less than or equal to 100. So one of the first things we have to know is we have to know how to translate words like no more than, at least, at most, less than, greater than, etc., and translate them into an inequality. So no more than 100 means that $100 is as big as it can get. So it has to be smaller than the $100, but it could be equal because it can be no more than 100. All right? And then what is no more than 100? The average cost. Average cost. So we take 80x plus 6,000 and divide it by x. Now, what was the rest of this problem about before we go about solving this problem? The rest of this problem was about explaining how they got to the average cost function. Lots and lots of, quote, story problems do that in algebra and mathematics. They have explanations of how to get to the formula. Now, from now on, you need to know that average cost is always total cost divided by the number of items. If you remember that, then you can always write an average cost function. And as you can see, the average cost function is a rational function, or creates a rational equation or inequality because it's a fraction. Okay? Now, as we learned before, when we set about solving these, we cannot cross multiply. We have to take rational inequalities and make them less than or equal to 0, which means we got to find and keep our common denominators. We can't clear fractions because, remember, if we multiply by the variable x, we don't know whether we have to turn the inequality around or not, because we don't know whether x is a positive or a negative. So you cannot do that. You have to kind of go about it in the way of doing 80x plus 6,000 over x minus 100 is less than or equal to 0. Now, by making it less than or equal to 0, we'll eventually be able to use the zero product property. So I'm going to shrink this a little bit, and we'll just, keep solving the problem at this point. So to finish solving, we got to get a common denominator. Our common denominator is x. So we're going to multiply 100 by x over x to get it with the common denominator. And that will give us 80x plus 6,000 over x minus 100x over x is less than or equal to 0. Since they're both over x, that gives us 80x plus 6,000 minus 100x all over x less than or equal to 0. And that gives us 6,000 minus 20x over x is less than or equal to 0. And now we can use the zero product property. And if you remember, again, from quadratics, the zero product property says if two things are multiplied or divided together and they are equal to 0, then one or the other is equal to 0. And that's what we have here. We have 60 minus 20x divided by x. So what that means is our critical points here are 6,000 minus 20x equal to 0, or x equals 0, okay? Now, what we notice is that x can never be 0. And if you remember from Algebra 2, this is an asymptote. It still divides our real number line up into solution areas. So it's okay to write that here. We just know from graphing and so forth that that'll be a vertical asymptote. So we come back and we solve each of these. So we get 6,000 equals 20x. Divide both sides by 20. And get 300 is equal to x, or x equals 0. So what does that do? That divides our number line, 0 and 300. And then what we know is that our graph has to always be above or below the axis at less than 0, between 0 and 300, and at greater than 300. These are essentially three solution areas, because these are the places where the graph will either cross the x-axis or not. And so we'll look at the graph later and we'll see that that's true. But in terms of algebraically solving, what we do at this point is we choose a test value. So we can pick like -1, 150, and 400. All right, picking a value. Then you plug that test value into the final inequality you had and see if it gives you a true or a false statement. So if we plug in -1, we get 6,000 plus 20 over -1. Is that less than or equal to 0? That is true, because that'll be a negative number. That's true. So that means this is a solution, all right, up to 0. And then we plug in 150. So 6,000 minus 3,000 over 150. Is that less than or equal to 0? Well, we'll have a positive divided by a positive. That's positive, so that's false. All right? So this is not a solution. And then plug in 400. So we get 6,000 minus 8,000 divided by 400. And that's a negative 2,000 divided by 400, which is a negative number. So that is true. So this region is a solution. So now we've done all the work for this problem, and from this number line, we can now write our solutions. And so, since we know it goes up to 0, this is a solution. And from 300, this is a solution. We know that this is negative infinity up to 0, or 300 up to positive infinity. Those are the regions. Now remember, infinity is an open interval always. Can we actually equal 300? Well, that just makes the numerator 0, which is fine. 0 is less than or equal to 0. So we would include that. But what about 0? Well, this was a case where you can't divide by 0. So that one is not included. And so there is our solution as an interval. It's basically x is less than 0 or x is greater than or equal to 300. So there's our solution in inequality form. Now, to summarize, we ended up having a rational inequality. We proceeded to solve that rational inequality using our typical zero product property method, which works for all quadratics and rational equations and inequalities. At that point, then, we wrote our answer in inequality notation here and interval notation here. You need to be able to recognize both. So what's the next issue? The question is, how many bicycles must be produced each day for the average cost to be no more than 100? So let's look at this answer. Well, we could produce a negative number of bicycles, which means we're not producing any at all. So this part of the solution right here, and I'll do this in red, gives us essentially no information at all. Well, it gives us information. It just tells us that if you don't make bicycles, your cost is obviously going to be less than $100, okay, if you don't make bicycles at all. So in the context of the problem, if I was just solving this equation, this would be part of the answer. But since I'm not just solving the equation, I'm trying to answer a question, this does not give me, it's extraneous to the problem. It's not a solution. It gives me no information. Everybody knows the average cost is 0 if you don't make anything. So therefore, in order to keep the average cost down, you have to make at least 300 bicycles. So when writing your solution, how many bicycles must be produced each day? You would write the number of bicycles that must be produced each day is at least 300. which is x greater than or equal to 300, or an interval notation, 300 to infinity. All right? Making the number of bicycles over any number 300 or greater will keep your cost less than $100, which means then you'll have the right kind of profit. So notice the answer to the question is different than the solution to the inequality. This is something you want to be aware of while you're working on the problems. Okay, let's go to the next slide. So it turns out that what's going to happen is most of the time they're going to give you the inequality. And so you're going to end up writing whatever that inequality is okay, and solving that particular inequality, okay? Now, they're going to give that to you in the problem. So the step where I showed you average cost and working that out, where I talked about the story problem part of it, that's generally not a part of your assignment. But I want you to be aware of it because I could make it a part of a test, a midterm later in the semester. I want you to be able to do some of that simple translation. Now, examples of problems that will be rational inequalities come from like problems that have formulas that are fractions. So gravity has a formula that's fractional. Concentration problems have typical fractional problems. Even rate times time equals distance problems, if you rewrite it as time equals distance over rate, all of a sudden that becomes a rational equation and then could become a rational inequality. So just beware of that. These are the types of real world problems. The other one is work type problems, where if you rewrite the formula, it becomes a fractional form, and then you can make it a rational equation or inequality. Okay? So I believe that's all I have for you today. You should be able to do this lesson. Good luck, and we'll talk to you later. Bye.